Okay, welcome to EGR445. In today's class, we will continue the discussion from last lesson and work out a bevel gear problem. So the first problem I want to work out is the bevel gears are designed. So bevel gear are designed and we have to check them, the gear pair, for dynamic and wear load. So our job is to check for dynamic and wear load. The properties of the gear and pinion are, so you have pinion, you have gear, number of teeth, on pinion are 21, number of teeth on gear are 60. Material for pinion is steel and for gear cast iron. Brinell hardness number BHN is 200 and 160. Allowable static stress is 85 megapascals and 55 megapascals. The speed is 1200 RPM and 420 RPM. And tooth is 14.5 composite, again 14.5 composite. So in this problem, the gear pair is given to us. So we have a pinion and we have a gear. And what we want to do is we want to check this pinion and gear for dynamic and wear load. So this is not a complete design problem, but it's a partial design problem in a sense that we have this gear pair and we just want to see whether it is suitable for analysis or application or not. So what we will do is we will follow the gear design procedure, and first and foremost, the shafts are at right angle. So shafts are at right angles. Now what we are going to do is we are going to assume M is equal to module. Module is equal to M. And then I'm going to find out the values of the pitch angle for the pinion or the semicone angle for the pinion and the values for the semicone angle for the gear. So for pinion is equal to tan inverse of number of teeth on pinion divided by number of teeth on gear. So tan inverse of number of teeth on pinion are 21 number of teeth on gear are 60 is equal to 19.3 degrees. Now, since both of these shafts are 90 degrees, 90 degrees is equal to theta pinion plus theta gear. So the semicone angle for the gear, which is theta gear, is equal to 90 minus 19.3, which is 70.7 degrees. Now please understand, 21 and 60 are the actual number of teeth. But what we need to do is we have to find out TE, which is equivalent number of teeth. And the equation to find equivalent number of teeth is equal to T divided by cosine of theta. So what I'm going to do is equivalent number of teeth on pinion, I'm going to call PEP, which is number of teeth on pinion divided by cosine of 19.3 TEG is equal to TG divided by cosine 70.7, and with this we should be able to get 22.2 and 181.5. Now these values are needed when we find out Lewis form factor. Now this is the difference between the bevel gear and the spur gear. In spur gear, whatever value we get for the cosine value for that spur gear is 0, because theta is actually 0 degrees. So cosine theta is 1. So number of teeth is equal to equivalent number of teeth. But in the case of bevel gears, the actual number of teeth are used to find out the equivalent number of teeth. However, the equation is going to remain the same. So what we are going to do in the next step is we are going to find out the tooth form factor or Lewis form factor for pinion. I'm going to call this as YP prime, and the equation we will use is the equation for 14.5 composite system, and the equation is 0.124 minus 0.684 divided by TEP, where TEP are the equivalent number of teeth on pinion. So 0.124 minus 0.684 divided by 22.26, and the answer is 0.093. Please note, this equation is the same equation for spur gear. But it doesn't matter, you can round it off. Your answer is not going to change significantly. So if you were to say 23, still your answer is going to be same. It won't it won't change the answer. So same thing. Now we have to find out the Lewis form factor for the gear. Again, 0.124 minus 0.684 divided by TEG. Now, in this particular case, why do we have to find out the Lewis form factor for the pinion and the gear? The reason for this is the material is not same. Pinion is made up with steel and the gear is made up with cast iron. So we have to find out of this two, which one is weaker. Either the gear is weaker or the pinion is weaker. So 0.124 minus 0.684 divided by 182, and that gives me 0.12. Now to check, so we have to check whether pinion is weaker. Pinion is weaker or gear is weaker. So to find out whether the pinion is weaker or the gear is weaker, we have to multiply the Lewis form factor by the allowable static stress. So sigma OP multiplied by Y prime P is equal to 85 multiplied by 0.09, that gives me 7.9. And for gear, sigma OG Y prime G is equal to 55 multiplied by 0.12, that gives me 6.6. So in this case, as you can observe, the gear is weaker. So gear is weaker. What it means is, for design purposes, we are going to use the gear and all the dimensions will be based, or the module is determined based on the gear parameters. So first we want to find out the torque. Torque is equal to T, which is P multiplied by 60 divided by 2 times pi times speed of gear. One thing I forgot to mention here is the power to be transmitted is 9 kilowatts. In this problem, they gave us that the power that needs to be transmitted is 9 kilowatts. So P is equal to 9, 10 to the power 3 multiplied by 60 divided by 2 pi multiplied by the speed of the gear, which is 420. So that gives me 204.6 Newton meter. So this is the torque that is transmitted by the gear. And our design will be based on this torque calculation. So from this torque, I'm going to find out the tangential load, which is WT, Wt is equal to torque divided by the radius, or torque divided by diameter by 2. And the answer is 2 times 204.6, converting that into Newton millimeter, divided by the radius, and the radius is diameter divided by 2. Diameter is module multiplied by number of teeth on the gear divided by 2. Something to note, in this problem, the module is not given to us. So we have to find out the module. But we know for sure that the pitch circle diameter of the gear is module multiplied by number of teeth. So in next step, I'm going to plug in these values. So I would get Wt, which is the tangential load, is equal to 2 times 204 multiplied by 10 to the power 3 divided by m multiplied by 60. And that gives me 6,820 divided by m, and the unit is going to be in newtons. So I found out the tangential load. Next step is to find velocity, which is the pitch line velocity. Which is pi times d times n divided by 60. And it depends upon the units. So in this particular case, diameter of the gear is in millimeter. That's why I'm gonna keep all the units consistent. So I have pi times module multiplied by 60 multiplied by speed 420 RPM divided by 60, and that gives me 1320 m millimeters per second. So this is the pitch line velocity. Now, at this point, something to consider. So here is something. We want to find out the velocity factor. Which is CV. In this particular case, the module is not known. So module is not known. So what value of velocity factor should we take? So what we are going to do is, we are going to assume, this is a design problem, so it's little bit of trial and error is expected. So I'm going to assume, and I could be wrong, assume CV is equal to 6 divided by 6 plus V. So I'm going to assume 6 divided by 6 plus V and see what velocity factor I get. One thing to observe here, the velocity is in meters per second. Here, the velocity is in millimeters per second. So I need to convert 6 divided by 6 plus 1.32 m, and that gives me the value of CV. Now, unlike helical gears or spur gears, in the case of bevel gears, the important thing is we need to find out the pitch, actually the length of the pitch cone. So what it means is, if you look at this pitch cone here, I need to find out this distance. So this is going to look like something like this. So I need to find out this value that will be used in the Lewis equation. So let's calculate that. L is equal to dg, which is the diameter of the gear, divided by 2, that gives me the radius, sine divided by sine of theta gear. So one thing that I want you to consider is this actually is nothing but a simple triangulation. So this is the length, this distance is the length. We are trying to find out this distance is d by 2. This distance is d by 2. So dg is m times tg divided by 2 multiplied by sine of 70.5, 70.7. And when we solve this, we get answer approximately 32 m, and the unit is in millimeters because this module is assumed to be in millimeters. Since the module is in millimeters, module time number of teeth gives you the diameter, that is in millimeters, and the cone length L is again in millimeters. Now face width B is equal to face width. And please understand, value of face width is needed to solve the problem. So we are going to assume face width is equal to the cone length divided by 3. This is assumed. And with that, B is equal to 32 divided by 3m. Now we have all the parameters that we need to substitute in the tangential load equation. So let's do that. Wt is equal to sigma O multiplied by y prime. This will be for gear, multiplied by B multiplied by pi multiplied by m multiplied by y prime. Actually, I would just, this is CV multiplied by L minus B divided by L. This is the same equation that we discussed in the last class for the tangential load of the bevel gears. But since we are designing the gear, this is for gear, this is for gear, and this is for gear. So we have to make sure that we are using appropriate values. So let's substitute the values. Sigma O multiplied by 0.12 multiplied by 10.67B, 67M, which is B. So this is sigma O, Y prime G, this is B, pi, M. CV value is in terms of M, 6 divided by 6 plus 1.32 M CV multiplied by 32M minus 10.67 M divided by 32M. So as you can see, you have M on the left hand side and you have M on the right hand side. This equation cannot be solved in a straightforward fashion. Just like spur gear problem and helical gear problem, this equation needs to be solved by trial and error, or you can program this equation in your TI-84 and get the value of M. M happens to be 4.5, which is approximately 5 millimeters. So the module is going to be about 5 millimeters. The face width B is equal to 10.6 multiplied by 5, which is approximately 54 millimeters. The gear diameter dP is equal to module, which is 5, multiplied by the number of teeth, 60, 300 millimeters. This is DG. And dP is equal to 5 multiplied by 21, which is 105 millimeter. Now the next step is we have to check for the dynamic load. So let's do that. Check for dynamic load. To check for dynamic load, we need the pitch line velocity V, which is 1.32 times M. So that is 6.6 meters per second. The next step is we can actually find out the value of tangential load, WT. So if you look at the value of WT, we found out the value of WT here, but this equation is in terms of module. So what I'm going to do is I'm going to substitute the value of module, which is 5 millimeters. So 6820 divided by 5 is equal to 1364 Newton. This is the tangential load. Now, at this point, we have to refer to table, and I'm going to give you a moment to look at table 28.7. So please take a moment, open the textbook and go to chapter 28, which is on spur gears, and refer table 28.7. I will pause here for a minute so that, because this is important. at table 28.7, I want you to locate first class commercial gear. First class commercial. These are standard gears. And for module is equal to 5 millimeter. Tell me what is the value of error action or cutter error. What is the value of E? So please refer to table 28.7 and tell me what is the value of E. Anyone? Just type it in the chat window. Yes, that answer is correct. Everyone got this value? 0.055 is the tooth error action. Now, what we need to do is we have to select value of K. And K for 14.5 means stay in that chapter. Just look at what is the value of K for 14.5 composite teeth. K value is 0.107. These values are for spur gear. The Young's modulus for steel, so pinion, which is pinion is made up with steel. So Young's modulus for steel, and Young's modulus for cast iron and with this we can find out the deformation or dynamic factor. So deformation factor is given as C is equal to K E divided by 1 divided by EP plus 1 divided by EG. Substituting the values, (0.055) divided by 1, 210, 10 to the power 3 plus 1 divided by 84, 10 to the power 3. You get the answer 353 Newton per millimeter. So now we have got the value of C. Now we should go back and use the equation for dynamic load. WD is equal to WT plus 21V, which is the pitch line velocity, BC plus WT divided by 21V plus square root of BC plus WT. Now WT is 1364. So please note value of WT is known. Plus 21 multiplied by V is 6.6. B is 54. multiplied by C is 353. Please note we calculated C over here, plus 1364 divided by 21 times 6.6 plus square root of 54, 353 plus 1364. And once you solve this, your answer is going to be 11.5 kilonewton. Now, once we know the dynamic load is 11.5 kilonewton, we have to find out the static load and the wear load. So for that, we have to go back, and at this point, I want you to go to table 28.8. So go to chapter 28 and look at 28.8. It is important to observe. It is important to observe that in this problem, the material is already selected. The gear is made up with cast iron. So what we need to do is we need to find out value of endurance strength for the cast iron with Brinell hardness number of 160. So find out for cast iron with Brinell hardness number BHN is equal to 160. What is the value of flexural endurance limit? So I'll pause here for a minute, and this is an important exercise. Just go to table 28.8, see cast iron, Brinell hardness number 160, and find out the value of sigma E. And please use chat window and tell me what is the value. Correct. The answer is 84 megapascals. Megapascals is also Newton per millimeter square. So what we need to do is we need to find out WS. So we need to find out value of WS. WS is given as sigma E multiplied by B multiplied by pi multiplied by M multiplied by Y prime G. Value of sigma E is 84. Value of B is 54. Pi multiplied by module 5 multiplied by 0.12. And now I want you to take a minute and please calculate this value. You will notice that if you actually plug in these numbers in your calculator, you will realize that unfortunately your answer will be around 8.5 kilonewton. And this is a big caution. Because check this out, our dynamic load is 11.5 kilonewton. Our dynamic load is 11.5 kilonewton. For gear to be safe, WS has to be greater than WD. But in this particular case, that is not satisfied. So please note, in this case, this design is not safe. So what do we do? Now there are multiple ways this problem can be solved. But unfortunately, in this particular problem, there are a lot of constraints. So what we are going to do here is, so let me point this out. So design is not safe. So the design is not safe because static load is less than dynamic load. So what options do we have? Typically, if the problem is open-ended, the first option would be increase surface hardness. So if problem was open-ended, and let me write this down. If problem did not specify or it was open-ended, then we can actually increase surface hardness. Surface hardness increase would get you sigma E increase. So if you increase the Brinell hardness number, so increase BHN, that would increase sigma E. But unfortunately, in this problem, Brinell hardness number is specified. The second option is see if we can increase face width. So can I increase value of B? Now, what happens when we increase the value of B? When we increase the value of B, if you look at the equation for WS, WS is sigma E times B multiplied by pi multiplied by M multiplied by Y G prime. Now, M value is the module. If we change module, if for some reason, if we change module, please understand with change in the module, your pitch circle diameter, dia, is changed. If module is changed. So what I'm going to do is, in this particular case, I'm going to say to make, there is one more option. You can actually change the type of cut. So we used something called as the first class commercial gears. We can use precision gears or change gear from first class commercial to precision. What happens if we were to change the gear from first class commercial to precision? Then the problem, what happens is usually the tooth error action drops down. So let me just, what happens is E drops down. When E drops down, please note value of C drops down. C drops down. If value of C drops down, the total value of dynamic load drops down. But when you do that, when you change the value of E, you will have to repeat the process here. So this equation, so if we change value of E, then we have to repeat calculations and find new WD and hope that this WD is less than equal to WS that we found over here. So at this point, clearly in this problem, Brinell hardness number cannot be changed. So unfortunately, this option we do not have. So out of option 2 and 3, which option you would like me to take? Which option should we follow? Should we go with option 2 or should we go with option 3? Option 1 is not available, Dylan, unfortunately, because if you look at the problem statement, the cast iron, the Brinell hardness number is given to us. The Brinell hardness number is specified. So unfortunately, we can't change. The option is we can go with 2 or we can go with 3. Okay, very good. So this option is acceptable. So what I'm going to do is I'm going to go with option 2. So let's try. So let's try option 2, which means increase face width, which is value of B. Now for this, we need to go back a step. And again, we cannot increase face width to an arbitrary value. We have to follow the design guidelines for the face width and see what would be the maximum possible value of the face width for bevel gears. And when you look at the design data book, typically they will give you the value for the face width. They will kind of tell you that the face width will be within certain limit. And I want you to look at, refer, and this is very important, refer page 1087 from the text. The face width values are given as 6.3 m to 9.5 m. 6.3 m to 9.5 m. Also, there is another guideline that L by B ratio should not exceed 3. So should not exceed 3. So if you look at the way we have worked out the problem, if you try option 2, in the first iteration itself, when we found out the value of module, we used L by B ratio is equal to 3. So can you see here at this step, L by B ratio is equal to 3. So we are at limiting L by B ratio. So if we were to try option number 2, since we are at L by B ratio is equal to 3, unfortunately, we cannot try option 2. So this option is also not available to us. So unfortunately, we have to go with the last option and we have to repeat the calculations. Now, some of you may say, would it be advised to go with the precision cut gears? In this particular case, not all the times precision cut gears are required. But this is sort of a tricky problem because the pinion is made up with a different material, gear is made up with a different material. That's why we have to go back and forth. We have to go back and forth to come up with the value. So unfortunately, in this particular problem, little bit of trial and error is needed. So what we are going to do in this particular case is we will go ahead and try the problem with option 3. So what happens in option 3? So now we have no other choice, but we have to go with option 3. In option 3, we are going to use precision cut gears. And as soon as I go with precision cut gears, again, go back to the table 28.7 and find out, yes, thank you, the error correction factor for precision cut gears, E, is 0.015. Please observe, this is about 1/3 of the earlier value. So the deformation or the dynamic factor is 0.107 multiplied by 0.015 divided by 1 divided by 210 10 to the power 3 plus 1 divided by 84 10 to the power 3. And when you solve this, you will get an equation. The answer is 96 Newton per millimeter. Please understand, in the previous case, the value of C was 353. Now the value of C is 96. So immediately the value became about 1/3. That means my dynamic load, the new dynamic load, WD, is equal to WT plus that the entire equation. I will not repeat the equation. I will just write this down. 1364 multiplied by 21.6.6 multiplied by 54 multiplied by 96 plus 1364 divided by 21 multiplied by 6.6 plus square root of 54 times 96 plus 1364 is equal to about 5.5 kilonewton. This 5.5 kilonewton is less. So can you see WD is now less than WS. WS is 8.5. Hence the design is safe. So now we have to follow the same process and check for the wear load. Okay, before I proceed further, everybody understood? We have to go through the iteration because unfortunately, in this particular problem, we had failure in the first part, and then we have to go through the iteration. Any questions here? I'm gonna give you a minute and see if there are any questions. So this is the trial and error that is quite common with design problems. Now let's go to the next part where we have to check for the wear load. So check for wear load. And again, we have to go back to the chapter 28, but now I want you to refer table 28.9. I want you to refer table 28.9. Look at gray cast iron with Brinell hardness number is equal to 160 and find out surface endurance limit. So just quickly go to table 28.9, gray cast iron, BHN 160, and you will notice sigma EF. So no. So check this out. And this is something important that I want you to keep in mind. There is sigma E and there is sigma ES. So please note, sigma E is different than sigma ES. This is the endurance limit. Which is inside the material, and this is surface endurance limit. Now, why these two? Okay, why these two are different? So if you look at the gear, the surface endurance strength is the endurance strength at the surface. So this is where you have sigma ES, and sigma E is going to be here. This is where sigma E is going to be. So surface endurance strength in this case is correct 630. Sigma ES is equal to 630 Newton per millimeter square. With that, let's find out the value of K. Value of K is sigma ES square sine of phi divided by 1.4, 1 divided by EP plus 1 divided by EG. Sigma ES is 630 square sine of 14.5, 1.4, EP is 210, 10 to the power 3 plus 1 into the power 3 is equal to 1.18 Newton per millimeter square. Now the next step is we have to find out the ratio factor Q and the ratio factor is given as 2 times TEG divided by TEG plus TEP. And here a word of caution, these are equivalent number of teeth. What this means is 2 times 181.5 divided by 181.5 plus 22.2. Answer is 1.78. You are welcome to round off number of teeth, but your answer would approximately be the same. And with this, we should be able to find out the value of WW, which is wear load, the wear load is given as dP, B, Q, and K, where dP is the diameter of the pinion, and we know the diameter of the pinion is 105. So it is super important to keep in mind wear load always calculated based on pinion dP. So dP is equal to 105. The face width is going to remain the same, which is 54. Value of Q is 1.78. value of K is 1.18. And when you solve this, your answer is 11.9 kilonewton. Please note WW is greater than WD. Wear load is greater than dynamic load, which means the design is safe. Any questions here? Any question on this problem? I would like to work out one more bevel gear problem. And then we will talk about worm gear design. Let me give you a break of 15 minutes. And after the break, we will come back at about 7:25. And I will work out the next bevel gear problem. So I'm going to stop here for 15 minutes. Okay, let's work out one more problem. And in this problem, I would like to do the shaft design. That way you will have an understanding of solving the design problem all the way to the shaft design. Okay, let's work out this next problem. "20-degree full depth involute gears. And they are at the shafts at right angles. The velocity ratio is equal to 1:3. What it means is one revolution of bevel gear causes 3 revolutions of bevel pinion. Now, the gears, the good news in this case is both these gears are made up with steel. So gears made of steel. And allowable static stress, sigma O, is 70 megapascal, which is 70 Newton per millimeter square. That is the allowable static stress. But there is a difference. So in this problem, pinion made with alloy steel and gear made with cast steel. So this is sort of a tricky problem. Even though they say that both the gears are made up with steel, there are different grades of steel that are used for pinion and gear. So this value that I gave you, 70 megapascal, is for the cast steel. This is for cast steel. And for alloy steel, sigma O is equal to 100 megapascals. This is for alloy steel. Now, what we need to do is do the gear design. The power that is transmitted is 37.5 kilowatts. Speed of pinion with 750 RPM. And we have to find first module, face width, pitch circle diameters, and the pinion shaft diameter. So the tooth form factor or Lewis form factor is given as y is equal to 0.154 minus 0.912 divided by TE, where TE is the equivalent number of teeth. So TE is equal to T divided by cosine theta. Face width B is equal to 1/3 of L. And they have stated that the pinion shaft overhangs by 150 millimeter. So in this problem, so if this is the pinion, this pinion and this is the gear, it is cantilevered, and this overhang is 150 millimeters. Now what we need to do is, first and foremost, we need to find out the module, the face width, pitch circle diameter, and once all these are determined, we can look at the forces on the gear shaft and then find out the shaft diameter. So once again, the gear shafts are at 90 degrees. So both the shafts are perpendicular to each other. So what that means is I should be able to find out the theta value of P, which is pinion. Theta P for pinion is tan inverse 1 divided by 3. That gives me 18.43 degrees. The pitch angle for the gear is equal to 90 minus 18.43 is equal to 71.5 degrees. Now at this point, the number of teeth on pinion and gear are not given. So we have to look at the guidelines that are provided for a minimum number of teeth. And I would recommend that you take this moment, just take a moment to go back and review quickly the information that is given in the textbook, where the minimum number of teeth are specified. So usually the minimum number of teeth for bevel gear, they are about 20. And so what we are going to assume, just as a first cut, we will assume the number of teeth, number of teeth on the bevel gear to be 20. And just to give you where this number is coming from, I want you to look at page 1087. And here there is a guideline that number of teeth, minimum number of teeth on pinion is equal to 48 divided by square root of 1 plus VR square. So if you substitute the values for this problem, this becomes 48 divided by 1. VR is 3, so 9. So if you look at 10, square root of 10 is about 3.4. So this becomes about 15. So I'm gonna say the minimum number of teeth. I'm going to assume number of teeth on pinion is equal to 20. And once I have number of teeth on pinion is equal to 20, the velocity ratio is given as 3. So number of teeth on the gear are going to be 60. So TG is equal to 3 times 20 is equal to 60. Now please understand, as the gear and the pinion, as gear and pinion are made with different type of steel, we have to check which is weaker. So to do that, first and foremost, find out the equivalent number of teeth on pinion, is TP divided by cosine theta P. TP is 20, cosine theta P is 18.43. Similarly, TE, gear, TG, cosine theta G, 71.5. So you will find out these values. This is about 21 and this is about 190. So with these values, we have to find out the Lewis form factor equation. (0.154) minus 0.912 divided by 21, which is 0.11, YG 0.154 minus 0.912 divided by 190, which is 0.149. So then we have to check sigma O multiplied by YP. This is for pinion, and that is 100 multiplied by 0.11, and sigma O times YG, Y prime G, for gear is equal to 70, 0.149, 11.1, and 10.4. So in this case, gear is weaker. So since gear is weaker, we have to design the gear. Following the same process, we have to find out value of torque is power times 60 divided by 2 times pi speed of gear, which is 37,500 times 60 divided by 2 times pi times ng, which is 750 divided by 3. And that gives me 1432 Newton meter. With that, we are able to find out the value of WT. WT is torque divided by the diameter of gear divided by 2, which is 2 times 1432 divided by m times 60. Now to convert this into millimeters, I will convert the torque Newton meter to Newton millimeter, and the answer that I have for WT is 47.7 10 to the power 3 divided by m newtons. Next thing is the pitch line velocity. Is equal to pi times dg times n divided by 60. Pi m cg and p, sorry, ng ng divided by 60 pi m times 60, which is the number of teeth, multiplied by 750 divided by 3 divided by 60. That gives me 785 millimeters per second. So this will become 0.785 meters per second. Once again, we don't know the velocity factor. So you have a choice. You can assume a velocity factor. Please understand, this is sort of a chicken and egg problem, because unless we know the actual velocity, we can't find the velocity factor. And unless we know the velocity factor, we can't find the module. And to find velocity, we need the module. So here is the issue. Right now, the velocity is expressed in terms of module. The velocity factor depends upon the velocity. We need velocity factor to find module. So this is sort of a chicken and egg problem. So in the last problem, we assume the velocity factor as 6 plus v. It is okay to assume velocity factor 3 divided by 3 plus v. And please try to understand, velocity factor is just sort of a guideline that is giving you an idea about how many times that load is oscillating or fatigue is taking place. So slight variation in the velocity factor is okay. So you can use this or you can use this. The last problem, we use 6 divided by 6 plus v. So I'm going to assume in this problem, CV is equal to 3 divided by 3 plus v. And this is just an assumption. So that we can follow the problem and then we can work out the numbers. So here it's going to be 3 divided by 3 plus 0.785 m as the velocity factor. And we need to find out the length of the pitch cone, which is diameter of the gear divided by 2 divided by sine of theta gear. Diameter of the gear is module multiplied by number of teeth, which is 60, divided by 2 multiplied by sine of 71.5 degrees. And when you solve this, your answer will be about 31.6 millimeter. So you now know the pitch cone length. So the face width B is equal to L by 3. So that is 10.5 times module millimeters. Now with this, we can use the expression WT is equal to sigma O times Y prime multiplied by B multiplied by pi multiplied by M multiplied by Y L minus B divided by L. And this equation, we already know these values. So I would plug in the values in this equation. WT is known, which is 47.7, 10 to the power 3 divided by m, 70, then 0.149 times the value of b, 10.5 times m multiplied by pi multiplied by module multiplied by, this is the velocity factor. The velocity factor, we assumed it to be 3 divided by 3 plus 0.78 m multiplied by 31.6 times m minus 10.5 times m divided by 31.6 times m. So please note, just like the last problem, this equation has only one unknown, but we need to solve this equation using trial and error, or you can program this inside your calculator. So, and once you solve this equation, you will get answer as 8.7. So I'm going to approximate this to 10 millimeter. So the module is approximately 10 millimeter. The face width is 10.5 times 10 is 105 millimeter. The PCD of gear is equal to 10 times 60, which is 600 millimeter. PCD of pinion is equal to 10 times 20, 200 millimeters. And at this point, ideally, what I would recommend is please proceed and check for dynamic load. So find what is the value of WD, just like the previous problem. Find out the value of static load, and then find out the value of wear load. And for safety, dynamic load WD has to be less than static load. Dynamic load has to be less than the wear load. If these conditions are met, then the design is safe. But what I'm going to do is, I would give this as an exercise, but I will work out the shaft design problem. So first and foremost, what we need to know is, we need to know the loads, what different types of forces they act on this pinion shaft. They have already given us that this shaft is overhang. So what I want to do is, I want to find out the magnitude of the radial load. I want to find out the magnitude of the axial load. And please note, there is a tangential load. This is actually acting in this direction. So what I'm going to do is, I will try to draw a three-dimensional view. So this is the bevel gear. On this bevel gear, we have a tangential load that is causing this bevel gear to rotate. And because of the pressure angle, you get the normal load that results into a component in the radial direction and a component in the axial direction. So you have the tangential load. So this is tangential. This is radial. And this is axial. And these loads, this three-dimensional loading actually acts on this bevel gear and they give you different movements. So let's find out the magnitudes of these loads. So first and foremost, tangential load, we already know. Tangential load is torque divided by the radius, and torque is 477 10 to the power 3 divided by the radius is 83.3. This is the pinion radius. So this is pinion. Because please note, in the problem, they are asking us to design the pinion shaft. And this is something important to note. Even though our gear was weaker and all the design was done for the gear, but in this particular problem, since they are asking us to design the pinion shaft, we are finding out the load, tangential load on pinion. This is the tangential. So when you do this, this gives you 5731 Newton. The axial force is given as Wt tan of phi times sine of theta p. So where this is the pressure angle and this is the cone angle. So this equation is 5731 tan of 20 degrees multiplied by sine of 18.4 degrees. This gives us 660 newtons. So this is the horizontal force or the axial force. I need to find out the radial force. So this is the axial. This is tangential. And to find radial load, WR is equal to WT tan phi. And instead of sine, I would use cosine theta p. So 5731 tan of 20 cosine of 18.4. That gives me 1980 newtons. So once again, let's look at the figure. So this is how the bevel gear is. On this bevel gear, we have a tangential load, we have a radial load, and we have an axial load. So WT, WR, WA. Now, one thing to observe that WA is giving a bending moment. So this is the shaft. So this is the center line of shaft. So now I want you to look at the bending moments that are given by different loads. This distance from here to here. So from here to here is 150. We also know this distance is nothing but radius of the pinion. So now it can be observed that there are different types of moments taking place. So for an example, if you look at the bending moment in the horizontal direction, you would observe that you have a bending moment which is given by WR multiplied by 150. Now I want you to observe there is a bending moment given by WA. So there is also a bending moment which is given by WA times RP when you were to look at in the vertical direction. So I'm going to draw this. So you have WA times RP and WR times 100. Now WA times RP, this bending moment, it's constant throughout the bending moment of the shaft. So this is in the, if you were to look at the front view, this bending moment diagram, if you were to look at the top view. But when you look at the, so there is, so just a second here. So here, let's assume that you are standing over here. If you are standing over here, then you will notice that the bending moment, these two bending moments will be in the front view. So these two bending moments will be in front view. And if you were to look at the top view, the top view, the bending moment is going to be WT multiplied by 150. That will be the bending moment in the top view. So in the front view, this force and this force is going to give you bending moment. Let me draw another figure that will make it clear. So you have WR and WA. These two forces give you bending moment in the front view. And if you look at in the top view, you will see WT in the top view. So what we need to do is we need to take these two moments into the account when we find the total bending moment. One thing that I want you to note, and this is super important, that moment given by WR is in this direction. So notice moment given by WR in this direction, but moment given by WA is in this direction. So which means these two moments are opposite of each other. So for that, So it is super important. And I will try to explain this once again, because sometimes this may not be clear. So observe this. So in front view, this is the front view. You have two forces. You have WA and you have WR. In the top view, you just have one force, which is WT. So look at the moment given by WR. The moment given by WR is this distance, 150, which is WR multiplied by 150. And look at the direction of the moment. This moment is given in this direction. However, look at the moment that is given by WA. WA is at distance RP. So this is given in this direction, WA times RP. So when we solve this, this is going to be 1976 multiplied by 150 minus 660 multiplied by 83.3. And the answer is going to be 241 Newton meter. If you look at the bending moment given by WT, this distance is 150. So this will be WT multiplied by 150. And this moment is gonna look like 5731 multiplied by 150. So your answer is going to be 6. So 57. Yeah, this will be 860 Newton meter. So now you have this moment in the top, in the front view, which is the moment in the vertical direction, and this is the moment in the horizontal direction. The total moment, M total, will be, since these two moments are perpendicular to each other, horizontal moment square plus vertical moment square. And when you plug in these values, you will see that your answer is 893 Newton meter. We also have the torque values. We know torque, which is 477 Newton meter. So we can find out the value of TEQ, which is square root of M total square plus T square square root. So this answer happens to be 893 square plus 477 square, and that gives you about 1013 Newton meter. Now in this particular problem, the shear stress is not given for shaft, but I'm going to assume it to be 45 Newton per millimeter square. This is just assumption. So we know tau is equal to T divided by J multiplied by R. 45 is equal to 10, 13, 10 to the power 3, pi by 32, d to the power 4. It's a solid shaft, so d by 2. And the only unknown in this equation is d, which happens to be 49.2 millimeters. So the shaft diameter is 50 millimeters. So this is how you will solve the problem. Okay, any questions on the bevel gear? Any questions on the bevel gear? So next part is discussion on the design of worm gear. So next topic is design. This is the last gear, design of worm gear. Now, what is the difference between the bevel gear and a worm gear? So if you look at the bevel gear, your shafts are at an angle. So in this particular case, the shafts are perpendicular to each other. But in the case of worm gear, you have a worm and worm wheel in this type of arrangement. So this is called as the worm wheel, or also called as wheel or worm wheel. And this is called as the worm. So what happens is this worm rotates and this worm wheel rotates. So if you look at the way these shafts are attached, in this particular case, the shafts are in plane. Shafts. These planes are out of plane. So you have a worm and the worm wheel. If you think about the worm, this is something similar to the power screw. This is similar to power screw. So what happens is you actually cut threads on a screw or on a shaft, and these threads, so let me show you sort of a bigger picture. And you have the worm, and you have the helical gears cut, and then there are gears on the wheel. So the biggest advantage of worm wheel drive is very high reduction ratio. And worm wheels are not back drivable. What it means is you can rotate the worm and worm will rotate. So here's the thing. You can rotate worm either in clockwise direction or counterclockwise direction, and wheel would rotate in clockwise or counterclockwise direction. But if you rotate wheel in either clockwise or counterclockwise direction, worm will not rotate. So this is very important. So this is just unidirectional power flow. So the power can go from here all the way here to out. This is how the power can flow. And this is a very important usage for load carrying equipment. So for an example, imagine that you have an elevator, and this elevator has, here there is a pulley, and here you have the gear transmission, and then you have the motor. And this is the gear transmission. And now there is this load, and this load is being lifted. And all of a sudden, when the load is in the middle, the motor loses power. So there is no power, power drops. So if you use bevel gear, if you use spur gear, if you use helical gear, the load will actually drop down because of its self weight. So what will happen is the load will drive the motor. But if you have worm wheel, so what I mean by that is, imagine if you have a wheel here and then there is a worm here, then the motor will not be back drivable. So which means if you raise the load and all of a sudden, if the power goes out, the load will be locked. It will not drop on its own. So unless you rotate the motor, or unless you rotate the motor shaft by some means, you cannot raise or lower the load. So that is the importance of worm wheel drive. And because of the high velocity ratio, high reduction ratio, with high reduction ratio, you get very high torque. And this is super duper important phenomenon. So for an example, if you have a motor that is rotating at say 1200 RPM, and you want to drive the shaft to 20 RPM, this very high reduction ratio will require multiple stages of spur gear or helical gear, or you may have to use a planetary gearbox, but you can achieve this high gear reduction using the worm wheel drive. Now recognize, with this significant reduction, you will get huge torque. So torque at the output is going to be significant. Speed would be less, but the torque would be significant. So these are the typical advantages of worm gear. But unfortunately, efficiency of the worm wheel, efficiency of the drive is low. What that means is there is significant amount of friction and power loss that takes place in worm wheel drive. So unfortunately, because the worm wheel drives, they consume, they have low efficiency, they generate significant amount of heat. So you have to make sure when you design the casing, you have to make sure that the heat is appropriately dissipated. Now, there are different types of worms and types of worm wheel. So if you look at the worm, there is something called as single threaded worm. Just like power screw, you have double threaded worm. You could also have a conical worm. And this is used in very special purposes. If you look at worm wheels, or also called as wheels, you can have a straight face wheel, You could have a hobbed wheel. You could have a concave face wheel. And it is very interesting to note that these verb wheel drives are used in power transmission, electric overhead cranes, or lifts, or load hauling transmissions. So it's very interesting how these worm wheels are used. And I would strongly recommend that you take a moment and go on to the YouTube and watch how the worm and worm wheels are cut. Worm is nothing but sort of a power screw. To the terminologies that we see in power screw, for example, lead, and then the helix angle. But in the case of worm, we call it a lead angle. So that lead angle is actually an important design parameter. You also have the lead. Then we talk about the tooth pressure angle. We have the normal pitch. We have the helical angle. We have the velocity ratio, and so on. So the concepts that we studied in power screws, they are applicable in the worm and worm wheel design. So I'm going to give you some terminologies or nomenclature. So terms. The first term is called the axial pitch. This is clearly the pitch in the axial direction. This is also called as the linear pitch. So if you look at the worm separately, this worm is going to look like a power screw. If you look at the worm, this is sort of going to look like a power screw. And it is similar to a power screw. So this is how a worm is going to look like. So if you look at the profile of the worm, this is how it's going to look like. And then you are going to have the total length of the worm is going to be LW, which is the length of the worm. Then you are going to have axial pitch, which is PA. Then you will have the diameter of the worm. Then you will have an outside diameter of the worm. And then you can have the helix angle. So let me write those down. So first you have axial pitch. Then you have the lead, which is the travel in one revolution. Then you will have the lead angle, which is nothing but the angle between tangent to thread helix and the normal plane. And if you look at the equation, you will see tan lambda is equal to lead divided by PCT. Next, we have tooth pressure angle. which is nothing but the angle made by the axis of the worm and the normal. So this is similar to the pressure angle. Then we have something called as normal pitch. So this is the pitch in the normal direction. Then we have the helix angle. Which is called as alpha. Then we have the velocity ratio. And velocity ratio is speed of the worm divided by the speed of the wheel. So please remember this, speed of worm. Worm is always going to rotate faster divided by speed of wheel. And the alternatively, this is an important relationship. Please understand, in the case of gears, we have number of teeth that is relating to the speed. But only in the case of worm and worm wheel, you have number of teeth on the gear divided by number of start on worm. So number of teeth on wheel divided by number of start on worm. So if you have a single start worm or if you have a double start worm, that number will be in the denominator. Please note, worm is like a power screw, so you don't have multiple teeth. You just have one start or two start. And then there are standard proportions, and then there is equation on the efficiency. And then what we do is we use all these relationships to design the gear, worm and worm wheel. The principles are the same. We actually look at the Lewis form factor equation. We look at the velocity ratio. Then we find out the static load. We find the wear load. But one important thing that is different, since the efficiency of the worm wheel drive is significantly less, what we have to do is we have to find out the heat loss. So what is the difference between the worm wheel design and the gear design? In the case of gear design, we don't explicitly find out the heat loss or heat dissipation capacity of the gearing. But in the case of worm and worm wheel, that is an important factor that needs to be taken into account. So what I'm going to do is I'm going to stop here today, but in the next class, I will give you the design guidelines or design process for the worm wheel and work out a few problems. If you have any questions, I would be happy to answer.